Hello everyone. Welcome to the lecture number 12 of General Topology. In the last lecture, that is in lecture number 11, we have discussed about continuous functions. We defined continuous functions and we discussed some results based upon continuous functions. In this lecture, we'll discuss few more examples of continuous functions and we'll discuss two more types of functions, that is open maps and closed maps. Before proceeding further, let us recall the definition of continuous function. Let x and y be two topological spaces. A function defined from x to y is said to be continuous if for each open subset V of y, the set F inverse B is open in X. That means if we have two topological spaces, x and y, and we have a function f from x to y, this function f is said to be continuous if for every open set V of y, f inverse V is open in X. In other words, a function f from x to y is said to be continuous if inverse image of every open set in y is open in X. Now let us prove that constant function is always continuous. Let f is a function from x to y, which is defined by f of x is equal to c for every x belongs to x. That means here f is a constant function. For every value of x in x, the image of x is c. We have to prove that this constant function is continuous. Here we have two topological spaces, x and y, and f is the function from x to y. And image of every point in x is c. So this function f is a constant function. All the points of x are mapped to one point c of y. Now we have to prove that this function f is continuous. To prove f is continuous, we have to show that inverse image of every open set in y is open in x. Now let us take an open set U in y. Since U is an open set in y, there are two cases. Either this point C belongs to U or C doesn't belongs to U. So if C belongs to U, then F inverse U is equal to whole space X, because this C is the image of all points of X. So inverse image of a set which contains C is whole space X. So if C belongs to U, then F inverse U is equal to X. Now the other case is if C doesn't belongs to U. If C doesn't belongs to U, then F inverse U is empty. So in both the cases we have seen that F inverse U is either X or it is empty. And this X whole space X and the empty set are open in X because X is a topological space. So here we have seen for every open set U of Y, F inverse U is always open in X. Therefore, the function f is continuous. So we can say that constant function is always continuous. Now one more statement is here. Composition of two continuous function is continuous. Let f and g be two continuous functions. F is a function from x to y and g is a function from y to z. We have to prove that composition of this f and g is a continuous function. That means we have to show that composition map G of f from x to z is continuous. To prove G of f is continuous, we have to show that inverse image of an open set in Z under the mapping G of f is open in X. Let us take an open set U in Z and we have to show that G of f inverse of U is open in X. Since U is an open set in Z and g is a continuous function from y to z, g inverse u is open in y. Here this g is a continuous mapping from y to z and u is a open set in z. So g inverse u is open in y. So here we have g inverse u is open in y. Also we have f as a continuous function from x to y. And here we have g inverse u is a open set in y. So we have an open set g inverse u in y and f is continuous from x to y. So f inverse of g inverse u is open in x. So here we have f inverse of g inverse of u is open in x. We know that f inverse g inverse of u is nothing but inverse of the composition g of f of u. So g of f inverse of u is open in x. We started with u as a open set in z, and here we get that g of f inverse u is open in x. So g of f is a continuous function. Now let us see this example. The absolute value function f on the real line R is continuous. Let f be the absolute value function on R. That means f of x is equal to mod x for every x belongs to R. That means f of x is equal to x if x is greater than or equal to 0, and f of x is minus x if x is less than 0. Graph of the absolute value function looks like this. Because as per the definition of f of x, if x is equal to 0, then f of x is 0. If x is equal to 1, then f of x is also 1. Because if x is 1, that means x is greater than or equal to 0, f of x is 1. And if x is equal to minus 1, then also f of x is 1. So here we can see that image of this point 1 is 1 and image of minus 1 is also 1. Similarly, image of 2 is 2 and image of minus 2 is 2. So if we ask that inverse image of 1, inverse image of 1 is 1 and minus 1. Because image of 1 is 1, image of minus 1 is 1. So inverse image of 1 is 1 and minus 1. Similarly, inverse image of 2 is minus 2, 2. In other words, we can say that for any x belongs to R, inverse image of x is plus x and minus x. Now to prove f is continuous, we have to show that inverse image of every open set is open. Since f is a function on R and R is having Euclidean topology or usual topology, any open set in R is of the form of an open interval AB or union of open interval. So three cases arises. Here we have f of x is equal to mod x. Now the case one is both of these endpoints of the open interval AB are positive. Case 2 is A is negative and B is positive. And case 3 is both A and B are negative. Now let us check what is the inverse image of this open set or open interval AB in all these three cases. Let U is equal to the open interval AB be an open set in R. Now let us check the first case. In the first case, both A and B are positive. Here we have the open interval AB, which is lying above the origin. That means A and B are positive. And we know that in the case of an absolute value function, inverse image of B is minus B plus B. F inverse B is equal to minus B and plus B. Similarly, inverse image of this point A is minus A and plus A. So, inverse image of all the points lying in between A and B is the points lying in between minus B minus A union all the points lying in between A and B. That means inverse image of the open interval AB is union of two open intervals. This open interval minus B to minus A union interval A to B. So F inverse U, where U is an open interval AB and A and B both are positive, then F inverse of U is union of two open intervals minus B minus A union interval AB. And since this is union of two open intervals, and we know that union of two open interval is a open set in R, F inverse U is open in R. Now in the second case, A is negative, B is positive. So here we have A, which is negative, and B is positive. Now let us check what is inverse image of this open interval AB. Now inverse image of this B is minus B and plus B. And all the points lying in between this 0 to B lies from minus B to 0 and from 0 to B. So inverse image of AB or inverse image of U where A is negative and B is positive is the open interval minus B to B. And this is an open interval. So F inverse U is open in R. So in case 2 also F inverse U is open in R. Now let us check the third case. In the third case, both A and B are negative. Since both A and B are negative, F inverse U is empty. And empty set is also open in R. So in all the three cases, we have seen that inverse image of U is open. Hence, F is continuous. So absolute value function on real line is continuous. Now let us define one more mapping, that is open map. A map F from X to Y is said to be an open map if image of every open set is an open set. Similarly, a mapping F from X to Y is said to be a closed map if image of every closed set is a closed set. That means if we take any closed set in X, then image of that closed set under this mapping F is closed in Y. Here we have an example. Let X is equal to 1, 2, 3 with topology tau 1 as empty set, whole space, set containing 2 points 1, 2, singleton set 2, and set containing 2, 3. And let Y be another set containing 3 points A, B, C with topology tau 2, which contains the empty set, whole space Y, singleton set A, and set containing 2 points A, B. Now let us define a mapping from X to Y. Define F from X to Y by F of 1 is equal to A, F of 2 is equal to A, and F of 3 is equal to B. That means 1 and 2 are mapped to the point A, and 3 is mapped to the point B. Now let us check whether this mapping is a open mapping or not. Here the image of every open set in X is open in Y, because here in X the open sets are this: empty set, whole space, set containing 2 points 1, 2, set containing single point 2, and set containing 2 points 2, 3. Now let us check what are the images of these open sets. Clearly f of phi is phi, which is open. F of the whole space is AB, because here 1, 2, 3 is in X. If we take image of 1, 2, 3, that is set containing 2 points AB. And this set containing AB is open in Y, because this is a member of the topology. So f of X is open. Now image of the third open set 1, 2. F of 1, 2 is equal to A, because these 2 points 1, 2 are mapped to the point A, and the singleton set A is open in Y. So here also image of this open set is open in Y. The next open set is 2, and image of 2 is A, and this singleton set A is also open in Y. So image of this open set is also open. And the last open set in X is set containing 2 points 2, 3. And image of 2, 3 is AB. And this set AB is open in Y. So image of the last open set is also open in Y. So here we have seen that image of all the open sets in X is open in Y. So this mapping is a open map. But this function or this map is not a closed map, because 3 is a closed set in X. 3 is a closed set in X, because complement of 3 is 1, 2, and 1, 2 is open. Now image of 3 is singleton set B. But singleton set B is not closed in Y, because complement of B is AC, and AC is not open in Y. So B is not closed in Y. So here we have seen that image of the closed set 3 is B, which is not closed in Y. So the function f is not a closed map. This mapping is a open mapping but not a closed mapping. Now let us show that the constant function on R is closed but not open. Now let us take the constant mapping. Let f from R to R be the constant function defined as f of x is equal to c for every x belongs to R. Now we have to show that this function f is closed but not open. Now for any open set u in R, f of u is equal to c, because f is a constant function. Image of every point in R is C. So image of this open set U is also C. So f of U is the singleton set C. But the singleton set C is not open in R, because R is having usual topology or standard topology. So image of a open set is not open under the continuous function. So it is not a open map. But for a closed set K in R, f of K is again the singleton set C, because it is a constant mapping. Image of every point is C. So image of this closed set is also the singleton set C. But the singleton set C is closed in R, because R is having standard topology. So this is a closed mapping, but not an open mapping. So this is all about in this lecture. In the next lecture, we'll discuss about homeomorphism.